Hey, welcome back to ClearSpot. Here's something most solar operators won't tell you. Your solar panels are degrading right now, not in 10 years, not when equipment fails. Right now, today, this hour, every single panel on every single farm is losing efficiency through one of 5 specific degradation pathways. And the scary part? Most of you can't see it happening until it's already cost you hundreds of thousands in revenue. In 2024, U.S. solar facilities averaged $5,720 per megawatt in losses, and much of that came from degradation nobody detected until it was too late. Today, I'm breaking down exactly what these 5 degradation pathways are, how fast each one destroys performance, and most importantly, how to spot each one before it ruins your year. Let's go. Imagine this. You just commissioned a beautiful new 50-megawatt solar farm. The tests pass, the systems are aligned, everything looks perfect. Then you turn it on, and in the first few hours of sunlight exposure, your panels start losing power. Not dramatically, but noticeably. That's light-induced degradation, or LID, and it's completely normal. Here's what happens at the molecular level. Your solar panels contain traces of oxygen in the silicon wafer. When sunlight hits for the first time, oxygen interacts with boron dopant, creating defects that reduce efficiency. The numbers. Typical LID causes 1 to 3% power loss in the first few hours to days of operation. This stabilizes within the first year, but you lose that power permanently. On a 50-megawatt farm, that's potentially $50,000 to $150,000 in unrecovered revenue right out of the gate. Why this matters for your acceptance testing? Here's the trap. If you commission your farm in December during cloudy weather and run acceptance testing immediately, you might pass with flying colors. Then January comes, clear skies, full sun exposure all day, and boom, LID kicks in. Your performance ratio drops 2 to 3%. Is it a problem? No. But your performance guarantee might think so. How to detect it? Compare your day 1 output to day 30 output under similar irradiance conditions. You should see improvement as LID stabilizes, not decline. If it's still degrading after 30 days, you have a different problem. The fix. Some manufacturers actually pre-season their panels, exposing them to controlled light and heat before shipping to minimize LID in the field. If your supplier does this, you lose less performance after commissioning. Most importantly, account for LID in your performance models before acceptance testing. Now we get into the scary stuff. Potential induced degradation, PID, is the most destructive degradation pathway I'm going to show you today, and here's what makes it terrifying. It's invisible until it's already destroyed your equipment. What happens? In an ungrounded or poorly grounded solar system, your modules develop a voltage potential relative to ground. That voltage difference causes ions to leak from the module materials. Electrons escape where they shouldn't. The module essentially starts short-circuiting itself from the inside. The damaged PID can destroy 20 to 30% of your panel's output power over 5 to 10 years. But in the worst cases, studies show 27 to 39% loss within just 4 to 8 months of operation. Let me put that in perspective. A 50-megawatt farm losing 25% capacity is $14 million a year in lost revenue. That's not a maintenance problem. That's an existential threat to your project economics. Who gets PID? PID primarily affects systems with high system voltages. 1,000-volt systems are at risk. Poor grounding or ungrounded systems, hot, humid climates, older module construction with poor encapsulation, and negative voltage bias relative to ground. Here's the industry secret. PID didn't used to be a major problem, but as the industry pushed for higher voltage systems and cut corners on grounding to save costs, PID became epidemic. How to detect it? This is where it gets scary. Traditional monitoring systems often miss PID completely. Look for non-functional black cells visible at the module frame, abnormally low string voltage compared to parallel strings, voltage that doesn't recover after shading or cloud cover, and performance decline that's visible but unexplained in your SCADA data. The fix. If you catch PID early, an anti-PID box, essentially a grounding device that reverses the voltage bias, can stabilize it. But here's the problem. It can't restore the damage already done. A module that lost 30% capacity will stay degraded permanently. Real story. A major European utility discovered PID on a 100-megawatt portfolio after 18 months of operation. The affected strings had lost 27 to 33% capacity. The anti-PID box stabilized it, But 18 months of lost revenue was gone forever. On a 100-megawatt farm, that's roughly $20 million in permanent loss. That's why PID detection isn't optional, it's survival. If PID is the silent assassin, LiTID is the hidden time bomb. Light and elevated temperature-induced degradation affects specifically PERC technology, passivated emitter and rear cell, which until recently was the most dominant solar technology on the planet. The discovery: engineers noticed something terrifying. Some PERC panels in the field were degrading 10 times faster than expected. We're talking 6 to 10% degradation in just 3 years. For comparison, normal degradation is 0.5% per year. LiTID-affected panels degrade at 2 to 3% per year in those early years. Why PERC modules are vulnerable? PERC technology involves a fast-firing step at extremely high temperature. This creates hydrogen-related defects in the silicon. Normally these defects are dormant, but under the exact conditions where solar farms operate, high heat, high light intensity, all day long, these defects activate. It's like the manufacturer accidentally built a time bomb into the most efficient panels ever made. The speed and severity field studies show, year 1 to 3, up to 6 to 10% degradation, some cases worse. Years 3 to 5. Degradation rate slows, but continues. Long-term, some recovery is possible, regeneration, but not guaranteed. On a 50-megawatt PERC farm, if you have 6% degradation in year 3 instead of 1.5%, you've lost roughly $3 to $4 million in revenue compared to what you were supposed to get. How to detect it? Here's the annoying part. LiTID shows as gradual, persistent PR decline over months or years. It's hard to distinguish from normal degradation or seasonal variation without multi-year data. Look for PR consistently declining beyond 0.5% per year. No obvious equipment failures, degradation accelerating in hot seasons, and performance improvement after cold periods. That's a regeneration indication. The fix. Unfortunately, there is no fix. Some manufacturers now pre-treat PERC cells to minimize LiTID, but for older stock, you're living with it. The industry response. This discovery essentially killed PERC as the dominant technology and accelerated adoption of TOPCon and HJT, heterojunction modules, which show lower LiTID risk and overall better degradation characteristics. If you're buying new equipment today, PERC is the old technology for exactly this reason. Okay, we've covered the molecular level disasters. Now let's talk about the damage you can actually see, or at least the damage that shows up clearly in thermal imaging. Physical degradation includes microcracks, hotspots, bypass diode failures, cell damage, and delamination. Cracks and cell puncture. These are hairline fractures in the silicon cells themselves. They can start during manufacturing, get worse during shipping, or develop from environmental stress. Thermal cycling, humidity changes, wind loading. The tragedy: a micro-cracked cell might produce 90% of normal power initially, so you miss it on commissioning day. Then over time the crack grows. Corrosion seeps in, the cell fails completely. Microcrack damage costs around 2 to 3% performance loss just sitting there invisible. Hotspots. A hotspot forms when one cell operates significantly hotter than its neighbors. Temperatures can be 10 to 20 degrees Celsius, higher than surrounding cells. Where do hotspots come from? Shading, even partial. Cell manufacturing defects, bypass diode failures, internal resistance problems, soiling, dirt concentrated on one area. Why hotspots destroy equipment. An overheated cell becomes a resistor. It consumes power instead of producing it. That power becomes heat. The cell can reach 70 to 80 degrees Celsius while surrounding cells are at 50 degrees. This accelerates degradation dramatically and in extreme cases creates fire hazards. Bypass diode failures. Every solar module has bypass diodes, typically 3 per panel, that protect against shading. When one diode fails, the entire substring, usually 1/3 of the module, stops protecting itself. That substring overheats and fails, potentially permanently. One failed bypass diode kills 1/3 of a module's output. Suddenly, that string is producing 33% less power. How to detect physical degradation? Thermal imaging, or IR, shows hotspots as localized temperature increases. A 50-megawatt farm can have thousands of modules, but thermal drones can survey everything in a single flight. Electroluminescence, or EL, Imaging is a different technique. You pass current through the panel and capture the light it emits. Microcracks appear as dark lines where current flow is interrupted. Defects light up like a map. IV curve tracing. Modern string monitoring equipment traces the voltage current curve of each string. Abnormal curve shapes reveal cell-level problems. String-level voltage and current monitoring. Compare parallel strings. If one string consistently underperforms its neighbors in similar conditions, you have a string-level problem. The fix. This is the good news. Physical degradation is often fixable. A failed bypass diode? Replace the junction box. A critically damaged module? Replace the module. A micro-cracked cell spreading? Replace the module before it spreads further. Unlike LID or LiTID, physical degradation doesn't condemn your entire farm to underperformance. It's a maintenance problem, not a structural problem. Last pathway is everything Mother Nature throws at your panels. Environmental degradation includes soiling, corrosion, backsheet failure, encapsulant breakdown, and moisture intrusion. Soiling, the simplest and most preventable degradation. Dirt, dust, pollen, bird droppings, salt spray all accumulate on your panels and block sunlight. The scope. Global soiling causes 3 to 5% annual energy loss, representing 3 to 5 billion euros in revenue loss worldwide. In desert regions, loss can reach 5 to 10% or more. Here's the thing. Soiling is highly regional. Coastal areas have salt deposits. Agricultural regions have dust from harvest. Industrial zones have pollution. How to detect soiling? Easy. Your radiant sensors will show normal sunlight, but your panel output is low. Compare a clean reference string against your farm average. If they diverge, you have soiling. Backsheet failure. Solar panels have a backsheet, the material protecting the cells from the rear. It's typically fluorinated polymer. Backsheet failure rates. 9 to 16% of modules experience backsheet problems within their operational life. When it fails, moisture enters. Corrosion accelerates. Delamination follows. Encapsulant degradation. The material between your cells and glass, called encapsulant, breaks down over time due to UV exposure, thermal cycling, and moisture. As it degrades, it yellows, becomes less transparent, and loses optical properties. Result: less light reaches the cells. Corrosion. In coastal or high humidity environments, aluminum frames corrode, connection points rust, copper traces oxidize. Electrical resistance increases, reducing current flow. The real killer here. Environmental degradation is permanent and progressive. A corroded connection won't uncorrode itself. A failed backsheet won't seal itself. Once moisture enters, it accelerates everything. How to detect environmental degradation? Visual inspection. Look for yellowing, cracking, discoloration, rust. Soiling sensors measure irradiance at 2 locations, clean versus farm average. String monitoring. Gradual voltage decline in all strings suggests soiling or environmental issues. Thermal imaging, salt spray and corrosion can create unexpected hotspots. Humidity sensors. If relative humidity inside sealed modules exceeds 40 to 50%, moisture has ingressed. The fix. This is prevention focused. Clean panels regularly for soiling prevention. Use high-quality materials rated for your climate. Ensure proper grounding and drainage to prevent corrosion. Use backsheet materials rated for 25+ years, not the cheap stuff. Install ventilation to manage moisture. So, we've covered 5 degradation pathways. Here's the practical reality. Your 50-megawatt farm probably has all of them happening simultaneously. LID, affecting your modules for the first 12 months with 1 to 3% loss. PID, potentially destroying hidden value if you have high voltage ungrounded systems, with 20 to 30% potential loss. LETHID, if you have PERC modules, 6 to 10% possible loss over 3 years. Physical degradation, probably affecting 1 to 3% of modules right now, with hotspots, microcracks, and diode failures. Environmental degradation, soiling alone costing you 3 to 5% annual performance. The stacking effect, a module that's LID affected, slightly PID susceptible, and physically damaged isn't losing 1% plus 0.5% plus 1% equals 2.5%. It's losing exponentially more, because each degradation mechanism compounds the others. That's why average farms lose 8% of possible production annually, and that number is trending upward. What this means financially. On a 100 megawatt farm generating $50 million annually, 8% loss is $4 million per year. Over 25 years, that's $100 million in undetected revenue loss. This is where AI agents change everything. Instead of waiting for annual PR reports or relying on seasonal performance ratio swings, intelligent systems can monitor LID progression in real time during commissioning, detect PID signatures and string voltage patterns before capacity collapses, track LID curves through multi-year data analysis, identify hotspots and microcracks through thermal pattern analysis, and quantify soiling losses through satellite irradiance correlation. At ClearSpot, we're building autonomous intelligence that doesn't just report problems, it predicts them before they destroy value. Here's what I want you to remember: degradation is not random, it's not mysterious, it's 5 specific mechanisms: LID, PID, LITD, physical damage, environmental stress, each with distinct signatures, each detectable, each preventable, if you catch it early enough. The operators winning in this industry aren't the ones with the biggest farms, they're the ones seeing problems 24 hours after they start, not 24 months later. LID happens at commissioning. Catch it immediately, with proper baseline testing. PID shows up in voltage patterns, your string monitoring should scream when it appears. LITD reveals itself through PR degradation curves. AI agents can separate LITD from normal aging within weeks. Physical degradation creates thermal anomalies. Drones see it instantly. AI analyzes it automatically. Environmental degradation masks itself through seasonal variation, but autonomous systems know what normal seasonal variation looks like, and flag true anomalies. The $10 billion that the solar industry lost in 2024 to underperformance, most of that was degradation losses nobody saw coming. The operators who captured that value were the ones who did see it coming. We're going to walk through exactly which data patterns correspond to which degradation pathways, and how to set up monitoring rules that actually catch problems. At ClearSpot, we're here to help you go from reactive maintenance to predictive intelligence. Because in solar operations, seeing the problem isn't just an advantage, it's survival. Thanks for watching. Let's optimize solar together. Like, share, and subscribe for more solar insights. ClearSpot. Smart device, smarter decisions.